So molecular orbital diagrams may seem like a very tricky topic, and it is at first, but it becomes much simpler when you know the rules, and it's actually not as tricky as it might seem at first. But first things first, a few important terms. So the first is the difference between a sigma bond and a pi bond. Sigma bonds only occur in single bonds, whereas pi bonds occur in double bonds and triple bonds. Now, the key thing to know is that the first bond formed is always sigma. So if you have a single bond, that's going to be a sigma bond. If you have a double bond, which is slightly shorter than a single bond, one of the bonds is sigma and one of them is pi. And if you have a triple bond, which is the shortest, one of them is going to be sigma, and then two of them, the other two, are going to be pi bonds. And so this sort of summarizes that. A double bond has one sigma, one pi, triple bond has one sigma, and two pi bonds. The other thing you should know is the difference between a bond and an antibond. So we know this before, we've seen this before. Bonds are stabilizing interactions. They lower energy, so they increase stability. It turns out that for every bond that is formed, an antibond is also formed. Now, antibonds are the opposite. They're destabilizing interactions, so they actually increase energy. And we'll write out both bonds and antibonds on our molecular orbital diagrams. The last thing you should know is that a given molecule can have one of two magnetic properties. It can either be diamagnetic, which means it has no unpaired electrons, or it can be paramagnetic, which means it has at least one unpaired electron. This is something you can only determine by drawing the molecular orbital. The other thing you need to know is how to calculate bond order. And bond order represents basically the number of bonds between two atoms. And so if bond order is equal to 1, you have a single bond. If bond order is equal to 2, you have a double bond. And if bond order is 3, you have a triple bond. Turns out that bond order doesn't have to be a whole number. It can actually be a decimal. So it can be 1.5, 2.5, etc. And these arise due to resonance. So we've actually seen resonance before when we drew the Lewis structure for CO3 2 minus. Basically, this double bond can be one of three locations: bottom left, top, or bottom right. And essentially, each of these bonds has partial double bond character. And so if we were to calculate the bond order of these bonds, we would get something between 1 and 2. And so that's how bond order doesn't have to be a whole number. And there is an equation you use to calculate bond order, and it's the following. So bond order is simply equal to 1/2 of the electrons found in bonding orbitals, so bonding orbital electrons, minus the electrons found in antibonding orbitals, so antibonding orbital electrons. You take the sum, you count the total of bonding orbital electrons, total of antibonding orbital electrons, subtract them, divide it by 2, and that's your bond order. Okay, so you've probably seen this before. It's in your course reader. There are two versions of MO diagrams, depending on what your atomic number is, or your Z. If your Z is less than 8, you're going to use the left MO diagram. And so you should memorize this arrangement. Whenever you draw an MO diagram, you should start with this. So start with your atomic orbitals, which is on the left and the right, with the 2s and then the 2p. The 2s combine to form a sigma bond and an anti-sigma bond. Remember, every time you form a bond, you also form an antibond. And then they also form these two pi bonds as well as a sigma. Now, really the difference between the left and the right is this. Everything else is the same. The order is switched. So on the left, you have the sigma bond above the two pi's, whereas on the right, you have the two pi bonds above the sigma. And notice that the antibonds are the same for both sides. So really, the first step to figuring out which MO diagram to use is to calculate the atomic number, the average atomic number. And sometimes the atoms are the same, in which case you only have to look at one of them. All right, so you should memorize these two arrangements. Okay, so let's draw the MO diagram for C2. We're going to calculate the bond order and determine whether it's diamagnetic or paramagnetic. So the first step is to figure out which version of the MO diagram to use. So we're going to figure out the atomic number of carbon, which is 6. And so because the atomic number is 6, it's less than 8. So we're going to use that first version, right? So we're going to use that first version, which looks as such. Carbon has 6 total electrons, but 4 valence electrons, and that's what you represent in these MO diagrams. And so on the atomic orbitals, which exist on the left and right, I'm going to label them as carbon. I'm going to draw on the 4 valence electrons. So 1, 2, 3, and 4. Notice how I follow Hund's rule in filling in the electrons. I do the same thing on the other side. Now that my atomic orbitals on the left and right are filled, I can fill in my MO orbitals, molecular orbitals in the middle. And so I have a total of 8 electrons, so I basically fill them as such. 1, 2, 3, 4, 5, 6. Notice how I fill these guys in. 7, 8. This is my MO diagram for carbon. To calculate the bond order, I simply take 1/2 of the electrons in bonding orbitals, which in this case is 2, 4, 6. And then I subtract by the electrons in the anti-bonding orbitals, which are the ones that are asterisked. So that's 2, and that gets me 1/2 of 4, which is 2. So really what that tells me is that the carbons are connected by a double bond. And here you can look to determine whether it's diamagnetic or paramagnetic. You just look to see if you have any unpaired electrons. Here, every electron is paired, so we call it diamagnetic. And that's it. So that's for C2. So let's try it for a different example, F2. So we need to calculate the bond order and determine whether the molecule is diamagnetic or paramagnetic. And so here the atomic number of fluorine is 9. And so it's greater than or equal to 8. And so we're going to use the second version of the MO diagram, which is the following, where the sigma 2p is lower than the pi 2p, x and 2py. And we just fill in the electrons as usual. And so for fluorine, the number of valence electrons is 7. So I fill that into the atomic orbitals on the left and right. So 1, 2, 3, 4, 5, 6, 7. This is fluorine. I also have a fluorine on the right. 1, 2, 3, 4, 5, 6, 7. In total, I have 14 electrons, so I fill them in as such. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so if I'm going to calculate the bond order, I simply take the number of electrons in bonding orbitals, non-asterisk orbitals, so that's 2, 4, 6, 8, subtract by the electrons in antibonding orbitals, which is 2, 4, 6, 1/2 of 2 is 1. And so F's are connected by a single bond, and here all the electrons are paired, so it would be diamagnetic. All right, and finally, an example of a heteronuclear MO diagram, meaning 2 different elements bonded together. Draw the MO diagram of OF, calculate the bond order, and determine whether the molecule is diamagnetic or paramagnetic. So here's the slightly tricky thing about heteronuclear. So the first thing you would do is the same first step you would always do, which is to calculate the Z. And here the elements are different, so you need to calculate the average Z. So for oxygen, the atomic number is 8. For fluorine, the atomic number is 9. The Z average is the mean of these two numbers, which is 8.5. That is greater than or equal to 8, so we use the second version. And so you might be tempted to use a version that looks like this. It turns out that for heteronuclear MO diagrams, there is a bit of asymmetry because the two atoms are different, and so the energy levels of their atomic orbitals are not going to be the same. So instead, what it's going to look like is something like this, where the arrangement of the MO diagram, the molecular orbitals in the middle is the same, but one of the atomic orbitals is lower energy than the other. And the one that is lower energy is the one that's more electronegative. So you always put the more electronegative element on the side where the atomic orbitals are lower energy. And here between O and F is more electronegative, so it goes on the right. O is less electronegative, and it goes on the left. Once you do this step, everything's exactly the same as what we've done for the homonuclear. So oxygen has a total of 6 valence electrons, so I put them in 1, 2, 3, 4, 5, 6. Fluorine has 7, 1, 2, 3, 4, 5, 6, 7. In total, 6 and 7 is 13, so I fill them in right down the middle. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? And so notice how everything's the same except one of these atomic orbitals is slightly lower energy than the other, and the one that's lower is more electronegative. And so bond order is going to equal 1/2 the number of bonding orbital electrons, which is 2, 4, 6, 8, minus the electrons in the antibonding orbitals, which is 2, 4, and then an extra one here, which is 5. That gets me 1/2 of 3, which is 1.5. So there's some partial double bond character. It's between a single bond and double bond. And we have one unpaired electron right here, and so we call that paramagnetic. And so that's an example of a heteronuclear MO diagram. You should know how to do both types of MO diagrams, and you should memorize the arrangement for all of them.